Okay, we wish we were hiking. I've given you a pretest. In this pretest, a crate is dropped from a helicopter, a hovering helicopter, straight down. And it lands in a very deep drift of snow. And during the time that this crate is still moving down through the snow, that's when you're supposed to answer these questions, okay? All of these questions pertain to the instant of time while this crate is still moving down through the snow. So with your neighbor, no, not with your neighbor, just you. Fill it out. Ask you, however, before you tuck it away, to write along the top, this may be wrong. I would hate for you to use this to study for the next exam, okay? Because I have a feeling that some of you have the wrong answer here. Now let's talk about the answers, and we're going to use this pretest throughout this week. I gotta tell you, if there was a day to miss lecture, it wouldn't be during this week. During this week, we're going to build the foundation of dynamics. Now, after this week, we're still going to be talking about Newton's laws, but we're mostly going to be practicing and practicing and practicing with problems that get more and more complex. But this week, we're going to build the foundation. And dynamics is what we do for the rest of 205 and all of 207. So it really is the wrong week to miss class. Let's talk about the first question here. The crate is moving down through the snow, so its velocity vector is down. But you weren't asked for the velocity vector, you were asked for the acceleration vector. The crate is slowing down, so the acceleration is up. And I suspect that every single one of you got that right. That's not a pretest. That's where we've been. This is the new stuff. That crate has a weight. Now what that means is you take that crate in, you put it on a scale in the post office, it says 50 pounds. You're paying for 50 pounds. That's the gravitational force the earth pulling down on the crate. 50 pounds, let's say. Now as that crate is crashing down through the snow, there's another force acting on that crate. In addition to the gravitational force, there's this force upward by the snow. Now the question is, how big should that be compared to the 50-pound weight of the crate? Should it be bigger than 50 pounds, equal to 50 pounds, or less than 50 pounds? Now, with your clicker, tell me how you just answered that question. A is the upward force by the snow is greater than the downward 50 pounds of the gravitational force. B, the upward force by the snow is equal to 50 pounds. C, the upward force by the snow is smaller than the 50-pound gravitational force. Okay, last call. We're all over the map. Now, folks, that's okay. That's okay because this is a pretest. That's the way it's supposed to be, okay? That's what we're going to talk about this week. Now, typically, we start with the discussion of motion, kinematics, and that's what we did in art class. It's not always that way, but most of the time in most classes around the country, that's where we start. And then next, we talk about forces, dynamics. Now, typically in most classrooms and in most introductory textbooks, the relationship between them is expressed that way. And if that's what you take away from this lecture, you will fail the next midterm. Have I got your attention? That is not the truth. What's up there is not the truth. The truth is subtly different. Watch. Oh, you want to see that again? Forces don't cause motion. Forces cause a change in the motion. And folks, it's that little subtle difference that makes all the difference. Okay? And we're going to try to make sure that everyone appreciates that. Now, before we can actually talk about forces in a meaningful way, we have to do some name calling. Not my favorite part, but it has to be done. So I've made a little table for you, a chart, and we're going to talk about the different forces that we will be using in this class. Now, folks, during the next little bit, you're going to get the impression that Greg is just really, really picky. That he likes things done his way. And that he's just kind of a little bit controlling. I assure you, none of that is true. Ask my family. I'm an easygoing guy. However, it turns out that whenever you are solving a dynamics problem, a force problem, the first step to every such problem is to draw what's called a free body diagram. So if I were drawing a free body diagram of, say, the Greg, I would draw all the forces acting on the Greg onto that diagram. I represent the Greg as a dot, big dot. And I add all the forces. Now here's the thing. If you start a problem with the wrong free body diagram, you have exactly 0% chance of getting the rest of the problem right. That means on the next exam, if you start a problem with the wrong free body diagram, you're wasting your time and your ink. Okay? So that free body diagram has to be right. Now, what I'm going to show you here is a recipe that will guarantee that every single free body diagram that you draw is 100% correct. If you follow this recipe, you'll never, ever get it wrong. Okay? I promise you. And that's why I am so insistent that we be picky. It's because I love you. I want you to do good. I really do. Okay? Now, we take all the forces, all the macroscopic forces in nature, and we divide them up into two classes, contact and non-contact. Now let me see if I can illustrate the difference. If I go outside with a picnic lunch and I sit my butt right down on the grass, right on the earth, we know that the earth is pulling on me with a gravitational force. My butt is touching the earth. I'm in contact with the earth. Is this gravitational force a contact force or a non-contact force? Non. Because we also know that we can take Greg to the top of the physics building, throw him off, and the earth is still going to suck him down. Okay? Yeah. You don't need that contact between the butt and the earth to have that force. It acts either way. Now, that's the way we're going to divide up these forces. If contact is required... Your name again, sir? Barrett. If I wanted to hit Barrett, I got to get right up here and just pow! I can't go back here. You feel that? Feel that now? There has to be contact in order for that force to be effective. Okay? But the gravitational force acts through space. Okay? And so that's our first non-contact force, the gravitational force. Now we're going to find that everything with mass, like this book, attracts everything else with mass, like this glass. But we're also going to find that that attraction is so minuscule, so tiny, that we can neglect it, unless one of the objects is huge, like the Earth. So we're only going to worry about gravitational forces exerted by the Earth on things. And we call those weight forces. So the first force I put on any free body diagram is a gravitational force, the weight force. It points towards the center of the Earth. I would label it with a W for weight. And every force is an interaction between two things. Things you can taste, smell, touch. There's a doer and a doee. Something is exerting the force and something is experiencing the force. This force would be by the Earth on the grid. Or I would sometimes just write it Earth, comma, grid. Now, again, it seems picky, right? If you label them this way, you will never get the wrong force on a free body diagram, and finding the third law of forces that we'll talk about on Friday will be a cinch. This is always going to be by, comma, on. The Earth is pulling on the grid. Now, the electromagnetic forces break up cleanly into electric forces and magnetic forces. Now in 207 today, we started our discussion of the electric force. It's a very rich subject. It's one of the better parts of 207. We're not going to talk about electric forces in this class at all. However, each and every one of you, I bet, has a refrigerator magnet holding things to your refrigerator. And you know that refrigerator magnets and refrigerators attract each other. We're going to deal with a magnetic force at that level. And we're going to call it a capital M. So, like the refrigerator on the magnet, or the magnet on the refrigerator. Now there's also a class of forces called nuclear, or nuclear, depending on who your president is. And we're never going to talk about those again. Those are the strong forces, the weak forces. They hold the nucleus together inside an atom. The weak force is involved in beta decay, different decay mechanisms. We're never going to talk about those. Now here's the beauty of this. Every time you draw a free body diagram, you're going to be worried about, well, did I get the right forces? Well, the first force you put on your diagram is the weight force, always. Then you ask yourself, are there any magnets to this problem? Usually not, sometimes. But once you've dealt with those two non-contact forces, all other forces have to be contact forces due to things that touch the grid. And so all you have to do is ask yourself, what's touching the grid? And for each thing that touches the grid, you ask, does it push or does it pull? Now let's talk about pulls. Chains pull, ropes pull, threads pull, strings pull. We call those forces the tension force, and we use a capital T to denote them. Now in 2 weeks' time, we're going to have a tutorial on tension. I call it the mother of all tutorials. It is just a thing of beauty. I've seen people weep over the beauty of that tutorial. I've seen a lot of people weep over it. Okay? Now, suffice it to say that if it's not a rope, it's not a chain, it's not a string, it's not a thread, it's not pulling. Okay? So let's talk about pushes. And in order to talk about pushes, I need everyone to do something with me. I need you to clear out a space in front of you, every single one of you, right now. Otherwise, you're not going to learn. I need you to push down on the table at some arbitrary angles, like 53 degrees, okay? Something arbitrary like that. Now I want you to memorize right now what you're feeling. And you should be feeling two different sensations. You should be feeling a pressure in your palm, and you should be feeling the skin pulled back on your bones. Do you feel that right now? I didn't say you could stop. Keep going, okay? Now you can stop. Lift that up. But now I want you to just lay your hand down, and with your other hand, push straight down perpendicular to the table until you feel that same pressure you felt before. Now folks, don't stop. While you're pushing down like that, there's something missing. That creepy feeling of the skin pulled back on your bones. So what I want you to do is, while you're pushing down, push your hand forward, edge it forward until you get that skin creeping back on your bone feeling. Got it? Okay, now you can stop. What we just did is take an arbitrary push and break it up into two pushes that are very different mechanisms. The first part is this part that was perpendicular to the table. Okay? Now that's what gave me the same pressure that I was feeling with the general push. Now what would I call a force that is perpendicular to the surface, that always points 90 degrees to the surface you're pushing on? What would I call such a perpendicular force? Pressure. Pressure is actually force divided by area, but we're going to find that that's equal to this force divided by the area. What would you call a perpendicular force? I'd call it a perpendicular force. But they didn't ask me. I wasn't alive at the time, and it turns out that it was named by mathematicians. And they named it the normal force. Because over in the math building, they don't quite understand what normal is. I've been to their parties. They're not normal. Okay. They think normal means perpendicular. And when they say, hey, you know, that looks normal, they're not saying it doesn't look abnormal. They're saying that looks perpendicular. So any force that is normal or perpendicular to the surface, we call a normal force. That's 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 a normal force. Now, folks, the normal force is the most common type of force. Whenever one thing pushes on another, there will always be a normal force. There may also be this other force that causes the skin to pull back on the bones, where the nooks and crannies of my hand are being grabbed by the nooks and crannies of the table. What would you like to call that force? Friction. And friction is one of the messiest forces that we have to deal with. We're going to spend a lot of time next week talking about friction. We'll find there's two different flavors of it. I call them the easy and hard kind, but everyone else calls them the kinetic and static kind. But for now, let's just recognize that it's the nooks and crannies of my hand grabbing the nooks and crannies of the table and vice versa. Now that general push was part perpendicular and part friction. Now if you ever wonder whether there's a friction component to a push, imagine greasing down the surface and asking yourself, could I push just the same as I did before? If you're pushing purely perpendicular and that table's greased down, no difference. But if you're trying to push with a friction force and it's greased, you can't do it. So that's how you can tell. If I look at this free body diagram of the grid, the Earth is pulling down on the grid. Are there any magnets? No, not yet. Be patient. What touches the grid? The floor. Does it push or does it pull? It's not a chain, it's not a rope, it's not a thread, it's not a string. Must push. Whenever one thing pushes on another, there will always, always, always be a normal force. There may also be a friction force. Now if I'm just standing here, do I need a friction force? I mean, if we grease down this floor, can I just stand here?
Yes.
Sure. But if I tried to walk, I'd fall on my face. So I need a friction force to walk, but to stand here, all I need is a normal force. See if your neighbor is on the bus with this name-calling thing. Now, for historical reasons, the friction force is given the symbol small f. And these are the 5 types of forces that we will be using on all of our problems. Every single force that we put on a free body diagram will either be one of these 2 non-contact forces, or it will be one of these 3 contact forces. You'll never put a force on a free body diagram that's just capital F. There's a force. No, it's got to be a certain flavor, and for each force you'll put what is it by, what is it acting on. And if you do that, I promise you this next section of the class will be so easy. So easy. Now, let's talk a little history. The first person to try to connect the forces to the motion was Aristotle. And this is a bad pixel day for him. But Aristotle did some experiments where he started stuff off and he found that it always stopped. Just every single time. He just kept doing these experiments and they just kept stopping. And that led him to postulate or suggest that stopped is the natural state of things. That here on earth things just want to be stopped. Now, of course, the heavenly bodies, they do different things because they're heavenly and they got different rules. But that was his take on things. Now, given that view, I would ask you, what's the velocity of this room? Well, relative to the sub, it's not moving, Greg. Right. But what if we do it relative to an alien that's just kind of hovering in a spacecraft above the North Pole? That alien would see the Earth going around once every 24 hours. And we would be going around with the Earth. And since everything's going towards Boston, and Boston's that way, this whole room is going that way. And we can figure out how fast it's going by taking the distance it travels, 2 pi r, and dividing by the time it takes to go once around, 24 hours. And that will give us about 400 meters per second. Now, folks, that's 900 miles an hour. We are going that way 900 miles an hour. Now, folks, if the natural state of things is stopped, I would ask you, if I jump up, why doesn't that whiteboard just smack me in the back of the head 900 miles an hour? And some of you after that last exam are saying, yeah, why not? That's the demo I'd pay money to see. Yeah. And the answer is, I'm also moving 900 miles an hour. That way. And I want to keep moving that way whether I jump up or stay on the ground. Now, the first person that suggested that was our old friend Galileo, the genius of the thought experiment. Now, Galileo did the same experiments that Aristotle did, but more carefully. He listened. Everyone listen. Did you hear the scraping? The scraping that goes on there? Well, Galileo suggested maybe if I polish that book and polish that table to a nice smooth surface, maybe if I start it the same, it'll go further. Now you remember Galileo was famous for pushing things to extremes. And so he said, what if I could make them perfectly smooth? What if I could get rid of all of the scraping, all of the friction? Would it stop at all? Well, he argued that the smoother he got it, the further it would go. And then he argued, if it's perfectly smooth, it's got to keep going forever. Now, Galileo could not get them perfectly smooth, and he had a disadvantage. and that is that he did not have a Smith's. I went down to Smith's this morning, and I got a block of dry ice. Now, does anyone know why we call this dry ice instead of wet ice?
Because it's ice.
What's that?
It sublimates.
It sublimates, okay? If you put it on your desk, it doesn't make a puddle. It goes straight into a gas. Does anyone have a quarter? Anyone? I got one. All right. Anyone got $20? I got two questions. Why does the quarter scream? And why does it stop? Talk to your neighbor. Why does it scream and why does it stop? Okay, why does it scream? Raise your hand.
Because it's the quarter is becoming cold at a very, very, very fast rate.
Okay, so the quarter is becoming cold, and at the same time the quarter is doing what to the ice? It's melting it, but with dry ice it sublimates into gas. And how does that gas get around the quarter? It has to escape, and it makes the quarter wiggle back and forth as it's escaping. Escaping gas has been a social problem for years. Now, why does it stop screaming? Yeah, at some point it becomes the same temperature, does it not, as the dry ice. And then it no longer turns the dry ice into gas. Now, the fact that this dry ice turns into gas allows me to get rid of friction. If I put it on a piece of slate, it turns out that it warms this dry ice so quickly that it creates a layer of gas underneath the ice. Now listen for the scraping sound. Did you hear any scraping? No. Now, we are a poor school. I had to get this out of an elementary school here in town. If we were a rich school like Harvard, we would have a piece of slate 3 miles long, perfectly level. And I would get this thing going, and what would happen? It'd just keep on going for 3 miles, constant velocity. It'd be cool. It'd be worth the tuition. Okay. Now, we're going to do something with that in just a moment. But right now, let's finish our story about Galileo. He did not have dry ice, but he had an incredibly great brain. And he used that great brain to figure out the answer we just observed. He used what we learned in the first tutorial and said that a ball going down a ramp has acceleration down the ramp. And the steeper the ramp, the bigger the acceleration. As I make that ramp shallower, the magnitude of the acceleration gets smaller. And then he jumped clear across to where the ball was going up the ramp. Now you've been to that first tutorial. What direction is the acceleration? Down the ramp. Now this is what Galileo did. He took these two cases here and he made those two ramps more and more and more shallow until they met at level. Now the more shallow he got this one, the smaller that arrow to the right became. The more shallow we got that one, the smaller this arrow to the left became. The only thing that he could figure out that it must be when they met in the middle was zero. And he knew what zero acceleration meant. He said it this way: an object at rest stays at rest. An object in motion stays in motion at constant speed in a straight line unless acted upon by a net force. So he, without the benefit of dry ice, said this thing's just going to keep on going forever. at constant speed, in a straight line, meaning constant velocity, meaning zero acceleration. Now, in one of the most profoundly suspicious coincidences in nature, the very same year that this genius died, this scary man was born. Sir Isaac Newton. He brought us the calculus. Let's just pause for a moment and give thanks. Now, he gave us a lot of things, including what we call the 3 laws of motion. Now, it turns out that the first law of motion, according to Newton, is that if there is no net force, there's no acceleration. And no acceleration means constant velocity. And we typically say Newton's first law this way. An object at rest stays at rest, and an object in motion stays in motion at constant speed. And wait a minute. That sounds suspiciously familiar. That's Galileo's law. And Newton acknowledged that it was from Galileo, and he said, I stand on the shoulders of giants. And I believe when he said that, he meant Galileo, because he carried on where Galileo left off. Now, the reason we call it Newton's first law is because it sets the stage for the second law and the third law. Newton's first law, Galileo's law, tells me when I can use Newton's second law. Now, it turns out that Newton's second law, I got to tell you, in 207, 2 weeks ago, we were talking about waves. And I was trying to get them to see the importance of the wave equation. And I said, guys, do you remember back in 205? You remember there was one equation that was more important than all of them? One equation to rule them all and in the darkness bind them? That if you could tattoo just one equation onto your body, it would be that one? Which one was it? And they all just immediately, Newton's second law. Newton's second law solves more problems in 205 and 207, and indeed in life in general, than any other equation. Okay? And the first law sets a stage for knowing when you're allowed to use the Newton's second law. So let's talk about Newton's second law. It deals with the effects of forces on an object. Now, folks, we're going to explore Newton's second law with an activity that is so trivial that I dearly want to ask Chat to turn off his camera. Okay? I'm embarrassed to have the doors open for fear that some of my colleagues will go by and see how trivial this activity is. And yet, I do this activity because the people who do not get the simple message of this little activity will fail the next midterm. The message of this simple activity is make it or break it. Now I want you to take that handout with the forces and turn it over. And you're going to see this table here. We have listed here certain motions. And for each of those motions, we're going to draw a velocity vector, an acceleration vector, and an arrow to tell us what push or pull is necessary. This is the key. Not to create the motion, but to maintain the motion. Okay? Now, the first one. Just the block of dry ice is at rest. If we have truly leveled this table, that's beautiful. What would you call that velocity?
0.
Yeah, what would you call that acceleration?
0.
Don't say 9.8. 0. Okay. So I've got 0 velocity, 0 acceleration, and I didn't have to do anything. Okay? Now the second one we've seen already. We get it started. It goes at constant velocity to the right. Okay? The velocity vector's to the right. The acceleration is, it's going at constant speed in a straight line. 0. And what did I have to do to keep it going?
0.
Nothing. It could be 3 miles long and keep on going. Now the next one, it moves to the right and speeds up. This is a little bit more tricky. If it's moving to the right and I want it to speed up, I got to push in the direction it's going. Now if this were 3 miles long and I kept pushing on it, it would keep going faster and faster and faster until I humanly could not keep up. Would have to have a robot doing it to keep pushing at the same speed. Okay, so it's moving this way. I want it to go faster, so I've got to push in the same direction. I told you this was trivial. What direction is velocity?
To the right.
What direction is the acceleration?
To
The right. What direction did I push?
the right.
To the right. One more time, be patient. It's going to the right and slowing down. I've got to push in the opposite direction it's moving. Okay, so what direction is the velocity? To the right. It's slowing down, so the acceleration is to the left, and I had to push to the left. Here's the simple message. Anytime something's moving, there's two important vectors representing that motion. The velocity vector is oh so visual. You can see it out the front windshield of your car. Big red vector. The acceleration vector is kind of more subtle. You got to think about it. You got to think, am I speeding up? Am I slowing down? Now, that table says that the force is intimately connected to one of those two vectors. That force actually causes one of those two vectors. Which one is it? Which one is it, based on that table? That's the message right there. The force is always in the same direction as the acceleration because the force causes the acceleration. Now people, the force is sometimes in the same direction as the velocity. By accident. By coincidence. There is no physics there. But this connection is ironclad every stinking time. If the acceleration is to the right, my net force has to be to the right. I have to have more force to the right than to the left. Okay? Force causes a change in the velocity, which is an acceleration. Not velocity, acceleration. Now, just for fun, let's suppose that we brought the first 3 rows up here and everyone was given a pencil with an eraser. And remember what you learned in that second tutorial. If we wanted this block of dry ice to go in a perfect circle at constant speed, and all of you people were gathered around this table and all you could do with your pencil was push, poke, how would you be poking this dry ice? What direction? Yeah, towards the center, perpendicular to the velocity. What if you wanted this thing to go around in a circle and speed up as it went? How would you poke with your pencil? Less than 90 degrees with respect to the velocity. And if you wanted it to go in a circle and slow down, you'd poke greater than 90 degrees. It just all comes together, doesn't it? It's all so beautiful. It's so much prettier than biology. Biology is just messy. Messy, messy, messy. Okay. So, here's the bottom line. A net force causes acceleration, not velocity. And a net force is the vector sum of all the true forces. Look at this diagram here. As I stand here, not moving, what's my acceleration? 0. That acceleration is caused by this free-body diagram. What that means is that this free-body diagram has got to scream 0. That means that if my weight force is 200 something, that this force has to be just as big. Okay? Because my diagram has to scream 0 for my acceleration to be 0. Let's take a more complicated example. What if I were to lift up that slate and make it into a ramp? And I put that dry ice back on and it speeds up as it goes down the ramp. Now if I draw a free body diagram for that block of dry ice, the first force I put on any diagram is the weight force. This is the earth on the block. I then ask, are there any magnets? No, not yet. So what touches the block? The ramp. Does it push or does it pull? It's not a chain, it's not a thread, it's not a string, it's not a rope. It pushes. Whenever one thing pushes on another, there will always, always, always be a normal force. And by normal, we mean perpendicular to this surface between the pusher, the ramp, and the pushee, the block. It's got to be perpendicular to that surface. And I label it ramp on the block. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. But if I have dry ice on slate, no friction. That's a free body diagram. I'm done. And not only that, I'm sure I'm done. I'm sure I didn't make a mistake because I followed the recipe. Now, which of those forces is causing the block to accelerate? Is it the gravitational force or the normal force? Both. It's both. It's the net or the total force. I've got to take those forces one at a time and add them. There's the plus sign right there. I take those vectors and I stack them head to tail. Once I've got all the vectors added together, the net force is just the vector sum. Okay, from the first starting place to the last ending place. Now the acceleration of the block is caused by that net force, and that means the acceleration has to be in the same direction as the net force. And we know in this case that direction is down the ramp. We've known that since the first tutorial. Okay? Now here's something very important. If I look at that table of forces, I don't see the net force on there. And that's because the net force is not a real force. It's a mathematical construct. It's the vector sum of all the real forces. I remember giving an oral exam to a grad student here for his doctoral work, and I was just having him do a free body diagram of a complicated situation. And I was playing devil's advocate, and I just said, so any other forces? And he'd find another force. Any other forces? He'd find another force. He got the free body diagram perfect. But did I let it go and say, good job? No. I said, any other forces? He looked all worried. Oh yeah, the net force. No. You never put the net force on a free body diagram. You only put the real forces due to real things that you can smell, taste, and touch. Now folks, let's go back to this pretest. Let's see if you learned anything just now. There are two vectors that describe the motion of this crate. The velocity down and the acceleration up. This free body diagram for the crate has to screen one of those vectors. This diagram has to cause one of these vectors. Which one is it? Don't say it out loud. Just tell me, is the upward force by the snow going to be greater than, equal, or less than the 50-pound weight of the crate if the crate is moving down through the snow and slowing down? Let's see if you got your money's worth today. Are you done? Be done. Good. 48 of you are on the bus. A blessing on your head. Okay? Now, here's the thing. This vector is oh so tempting because we can always see it if we've got any kind of imagination. But the success you will find on the next midterm will all be in ignoring that vector and concentrating instead on this vector. You have to ignore the velocity and recognize that this diagram has to screen that acceleration. If the acceleration is up, I've got to have more force up than down. The extra force up we call the net force. Okay? How much extra force up we have, more than we have down. Folks, that's a good stopping place. Again, don't miss Wednesday or Friday. We're going to be talking about Newton's second and third law.